Alright guys, today's lesson is going to cover significant figures and writing in scientific notation. So our objectives for this lesson are to know that significant figures show the precision of a measurement, to be able to count the number of significant figures or sig figs in a given number, and use the rules for sig figs to report calculations to the correct number of significant figures. Included in that, we'll also be looking at how to convert to and from scientific notation and what that actually means. So significant figures tell us the precision of a measurement. In our example here, we have a graduated cylinder and a beaker. And we're going to talk a little bit about the difference in precision of these two pieces. If you look, our graduated cylinder has small increments marked along its graduation. So you can see each of those lines probably represents 2 milliliters. Whereas in our beaker, we have lines in between, but each one of those lines is going to represent about 10 milliliters. So they aren't going to be as precise in terms of measuring. So that graduated cylinder is capable of measuring volume in 1 milliliter increments. In comparison, that beaker is going to measure volume in 10 milliliter increments. The graduated cylinder is more precise, so when you take a measurement from it, you're going to have more significant figures in your answer. The last significant figure is always an estimate and goes one digit beyond what the equipment is marked for. So for example, with the graduated cylinder that can measure in 1 milliliter increments, your answer should be to the 10th place, because you're going to estimate one spot beyond what the graduated cylinder is capable of measuring for sure. In comparison with the beaker, you're going to estimate to the ones place, because it can measure in multiples of 10. So for a graduated cylinder, you would read the volume as 11.3 milliliters, compared to a beaker, which would be just 11 milliliters. So these are a couple of the major rules for significant figures. When we say non-zero, we mean a number that is not zero. In other words, anything from 1 to 9. Leading zeros, those are zeros in front of a number. For example, 0.007. Those two zeros are called leading zeros. And then leading zeros to the right of non-zeros are also not significant. So for example, in the number 1000, those 3 zeros are not considered significant digits. That being said, I don't want you to focus too much on these rules, because I'm going to show you a shortcut. So in order to use this shortcut, you need to know a little bit of geography, starting with the location of the Pacific Ocean compared to the Atlantic Ocean. So if you didn't know already, we are over here on the west coast, have the Pacific Ocean to our left, whereas the Atlantic Ocean is on the east coast, or on the right side of the continent. So we're going to use that to help us remember what to do when we have a decimal that is present or absent. So if we have a decimal that is present, you're going to start from the left and begin counting at the first non-zero. So for example, if my number is 1.023, on the left side, because it says to start from the left, which is where the Pacific Ocean is, the first number that I run into that is not a 0 is the number 1. I'm going to start counting there and count all the way to the end of my numbers. That's 1, 2, 3, 4 sig figs. I'm going to abbreviate that SF. On the other side, if my decimal is absent, I'm going to start counting from the right, because the Atlantic Ocean, also starts with an A, is on the right side of the continent. So for example, if my number is 1,200, and I start counting from the right side, the first number I run into that is not a 0 is that 2. So that would be 1, 2 sig figs. And it's easy as that. Okay, so we're going to take a moment to practice. I want you to go ahead and pause the video here so that you can jot these numbers down and try and count the significant figures correctly. Once you've done that, go ahead and resume and we'll walk through the examples together. Okay, let's take a look at our examples. Starting with this first number, we do not have a decimal, so our decimal, in other words, is absent, which means we're going to start counting on the right side of the number. The first number that is not a 0 is the number 4, which means this has one significant figure. In my second example, I have a decimal, which means I'm going to start from the left side. As I go from left to right, the first number that is not a 0 is the number 4. So I'm going to count 1, 2. That'll be two significant figures. Continuing on, I have another number that has a decimal that is present. So starting with the first number that is not 0, in this case a 9, it's 1, 2, 3 sig figs. Now this next one is a little tricky because it didn't get displayed correctly. This is actually a number in scientific notation, so this should be written as times 10 to the 24th. And what you need to know about that is we don't care about this portion of the number in terms of significant figures. So I'm going to treat this just like a normal number like we've been working with. I have a decimal that is present, so I will start counting on the left side. So starting from the left, I have 1, 2, 3, 4 significant figures. And then in my last example, I have 1, 2, 3, 4 sig figs, starting from the left. And that's it. We're now going to look at a couple examples of rounding numbers to a given number of significant figures. For example, in this first one, we're going to round all of these numbers to 3 sig figs. In my first number, I do not have a decimal, which means that I'm going to be starting from the right side when I count this number. Now, that means that none of these can be significant. So I'm going to need to take a look at this spot right here to round my answer. The number preceding the 3 is the number 4, which is going to cause this to round down. So my answer will round to 123,000. And if you double check, you will see that that is indeed 3 significant figures. Go ahead and pause for a moment and see if you can round the other 2 numbers in these examples to 3 significant figures. When you're ready, resume and we'll take a look at them together. Okay, so this next one, I want 3 significant figures again. No decimal. So I'm going to look at 1, 2, those are the 3 sig figs I'm looking for. This 9 is going to round that 4 up to a 5. So this is going to round to negative 235,000. And double checking that is indeed 3 sig figs. My next example, I do have a decimal. So I'm going to start looking at all of the digits that follow that decimal. This is going to be 1, 2, 3 sig figs. That 4 is not enough to round the 1 up. Remember, in order to round up, it needs to be 5 or greater. So this is going to round to 0.231. And that gives me the correct number of significant figures. Remember to be very careful when you have a decimal. You cannot add zeros after that because those are going to be considered significant. So make sure when you're working with decimals, you don't add in those extra zeros that you rounded off of your number. When you're doing calculations with sig figs, your answer should have the same number of significant figures as the measurement with the fewest significant figures. Numbers that are exact, like the number of inches in a foot, in other words 12, are not included when determining significant figures. So if you have something exact, you're not going to include that when you're trying to determine the fewest number of sig figs. Constants, such as pi, are also not included when we're determining sig figs. So let's go ahead and take a look at a couple examples. So for each of these, we want to solve them to the correct number of significant figures. I'm going to start by figuring out how many significant figures that should be. So in option A, I have decimals present in both my numbers, which means for both of those, I'm going to start counting from the left side. So this first one has 3 sig figs, and my second number has only 1 sig fig. Now I need to do a little bit of math. So 0.667 divided by 0.3 is equal to about 2.223, and that 3 is repeating. Now, I know that my answer needs to match the fewest number of significant figures. So in that case, that's going to be 1 sig fig. So this is going to round to 1 significant figure. This 2 isn't going to affect that, so this will round to just 2 for my answer. And remember, you don't want to put a decimal or a 0 there because that will add sig figs to our answer. For my next one, I have 1.3 times pi. Now remember, constants like pi are not included when we're determining sig figs. So I'm just going to look at my first number, which means I'm going to have 2 significant figures in my answer. So if I multiply 1.3 by pi, I'm going to get 4.08407, and I'm not going to continue writing that because I already know I should only have 2 sig figs in my answer. So that's 1, 2. That 8 will round the 0 up. So this will round to 4.1 for my answer. When doing addition and subtraction with significant figures, your answer should be rounded to the same number of decimal places as the least precise. So we're not technically looking at sig figs here. We're going to look at the number of decimal places. Exact numbers, such as the number of inches in a foot, are not included. And constants are also not included. So same rules as multiplication and division for those 2 things. So let's take a look at my 2 examples. In my first example, and again, we want to do least number of decimal places. That's going to be the second one. That's only 1 decimal place, or to the 10th place. So when I subtract that, the answer I get is 1.367, and I know I need to round this to the 10th place. That 6 will round the 3 up, so this is going to round to 1.4. In my second problem, I have, this is 2 decimal places, this is 2 decimal places, but this is only 1 decimal place, so I'm going to have to round to the 10th place again. And that actually works out because when I add those together, I'm going to get 5.2, which is actually already rounded to the correct number of significant figures. Now we're going to talk a little bit about scientific notation. Scientific notation is an alternate way of writing numbers. We usually use this when we're writing very large or very small numbers. Generally speaking, you're going to use scientific notation if the number you're working with is either equal to or greater than 1,000, or equal to or less than 0.001. And then just a note, you do not use scientific notation when you're dealing with money or temperature. So there are 2 parts to a number written in scientific notation. The first is called the coefficient. It's the number before the times 10. That coefficient must be greater than or equal to 1 and less than 10. The second part of that is called the exponent. And the exponent is the number after the 10 right here. That number is positive if the original number is very large, and negative if the original number is very small. So this answer here is actually equal to 0.0037. That negative number tells me that this is a very small number. When you convert to scientific notation, you're going to count the number of times you move the decimal to get to the correct coefficient. this number of times is the exponent. Your exponent will be negative if you move to the left, and positive if you move your decimal to the right. So let's take a look at a couple examples. In this first one, I have 3,500. I'm going to move my decimal here 1, 2, 3 places to get that to a number less than 10. So this will be 3.5 times 10. And I moved that 3 times, so that'll be times 10 to the third. And I moved my decimal to the left, so it will be a positive 3. In my next example, I'm actually moving my decimal 3 places again. This will be 2.34 times 10 to the third. Notice in both of these cases, I dropped these zeros from my answer. Remember with decimals, when you have a decimal there, that's going to make the zeros at the end of your number considered significant. And we know by looking at this original number that those are not significant zeros. Okay, in my next example, I have a number much smaller than 1, so I need to move my decimal to the right. This will be 1, 2, 3, 4, 5. So this will be 5 times 10 to the negative 5, since I moved my decimal to the right. In my last example, I need to move this 1, 2, 3 times. So this will be 2.356 times 10 to the negative 3. Now when we're trying to do the reverse, we're going to have to start by looking at whether our exponent is positive or negative. If my exponent is positive, I'm going to move my decimal to the right. We're adding zeros after the coefficient, so we're making our number larger. If my coefficient is negative, I'm moving the decimal to the left. And that's going to put zeros in front of the coefficient, making our number much smaller. So, for example, if I have 1 times 10 to the 5th, here's my 1 and my invisible decimal. That's going to be 1, 2, 3, 4, 5, and I'm going to fill those spaces in with zeros. I'm going to repeat that for my next one, and I'm moving it 4 spaces to the right. So 2.5 becomes 1, 2, 3, 4, and I fill those in with zeros. That's now 25,000. In my next example, I have a negative 5. That means I'm going to be moving my decimal to the left and making a smaller number. So I'm going to start by writing my 3 over here. And I'm going to move my decimal 1, 2, 3, 4, 5 spaces. And fill those spaces in with zeros. Last example. I have 4.2. I need to move my decimal 2 places to the left. So 1, 2. That becomes 0.042. That's it for significant figures in scientific notation. We will practice this more in class. Make sure if there were questions or concepts that you didn't understand, you jot your questions down in your notes, and we will address those in class.